These equations are completely against your intuition, unless your intuition is really good or really messed up twice over. So I'd probably click on the latter. Okay. So let's see. How do I want to say this? Let's see. Okay. Here's a crazy thing. Right? Here's a tube. Right? Here is a tube. I'm going to draw the actual thick walls of the tube to make it clear, to make this real. Okay? Here is a tube. You have point 1 here and point 2 there, like we just said to do. Right? But what's interesting is under our assumptions, to get flow, you don't need P1 to be greater than P2. What? Let's see, over here we have P1. Over here we have pressure 2. Over here the gas is flowing at V1. Over here the gas is flowing at V2. Over here we have area 2. Over here we have area 1. Is there anything else? Let's see, I don't think so. What is that? Did I just get hyper? Oh, that's the 1. Okay. There we go. So your intuition says the only way that anything's going to flow down that pipe is if the pressure on the left side is higher, right? You're thinking of the real world. You're not thinking of the assumptions, right? Under our assumptions, we assumed no loss. So Newton's first law says the fluid keeps going. Okay? So you could ask, well, if there's no pressure difference, why is it flowing in the first place? And the answer is something back here made it flow. Okay? When you calculate pressure differences for the homework assignments we're going to give you, the pressure difference you're calculating is not responsible for the flow. We're just saying there is a flow. Some compressor over here made a flow. Okay? And we can show you. Let's do this homework problem right now. Let's see. What is delta P? Oh, let's do it. Let's apply this crazy equation here. Well, we have position 1 and we have position 2. At position 1, what do we start with? P. Okay? P1 plus rho g y1, how high it is. Okay? Plus 1/2 rho v1 squared, how fast it's going. Fine. Okay? That must be the same on the other side. P2 plus rho g y2. Right? Rho g y2 plus 1/2 rho v2 squared. Okay? So you'd say these are the same. y1 equals y2, samesies. Okay. All right, those are the same, so they go away. Okay? Now, you'd think, oh, well, you're wrong. The pressures can be different because the velocities could be different. But can the velocities be different? No. Continuity. Continuity says A1 V1 equals A2 V2. And the way I drew it, A1 and A2 are the same. So A1 equals A2 equals A, so V1 equals V2. Right? You can't just arbitrarily have it speed up and slow down because of continuity of the volume. Right? So those velocities are equal. Sorry, oh my God, I got to stick to my cursive. Oh, those are velocities. All right, area, oh my God, this is area times volume is nothing. I forgot that I have two V's going here. There we go. Okay, so those velocities are equal. What does that mean? Those are the same. So we get P1 equals P2. Okay? So under our ridiculous assumptions, liquid can flow down this tube. Something out here got it going. And it's just like a mass on a frictionless table. It just flows through the tube because we didn't let there be any friction. Right? That's all it is. This is 1D kinematics. Conservation of momentum is all that is.